Good morning, everyone. Thank you for being here on such a lovely Sunday morning in Berlin. Today, I will talk to you about privacy-preserving data sharing in general. And so the whole morning, the whole track was about data privacy and ethics of data science. And this is exactly in this theme. A little background about myself: I'm leading the data science efforts at Status, and mainly working on exactly this, so privacy-preserving data sharing. And I want to share with you some of the learnings that we had dealing with this topic, and what we see that is done today in the privacy-preserving preservation field. The talk will be introductory, so if you're not familiar with data privacy mechanisms, hopefully you would get pointers to go and explore further for things, how not to do things and how maybe to do things. So I'll start by introducing the privacy notion, why is it important, and then delve more into the mechanisms that have been used or still in use in order to share data sets. Some of them are kind of not a go-to things anymore. So I'm going to show why not to use them, while others are kind of more trendy these days and constitute the state of the art. So, what is privacy? According to the English dictionary, privacy is a state in which one is not observed or disturbed by other people. Some consider it a fundamental right, and this for several reasons. And one most important reason, I would say, is that a lack of privacy induces behavioral changes in individuals, and as a consequence, change in how the society works in general. So to the right, I'm showing here a picture of this design. The Panopticon is Panopticon. So this is a prison design, and basically the cells are disposed in a circular fashion with a watchtower, single watchtower in the middle. And the idea is that if the prisoners think they may be observed in any single point in time, even when they are not observed, they actually behave as if they were observed, and this is actually changing their behavior. And because of this type of reasonments, we have some mechanisms in our free societies that guarantee the freedom of choice in the actions we choose to make. And for instance, anonymous voting is basically guaranteeing that each and every one votes for the person or for the idea that he thinks right, and not for because of fearing of some consequences. So today, when we talk about privacy, mainly in the digital era, we realize that most of our actions, when we use digital communications, are logged, are tracked, are used in a variety of ways. So websites that we browse, the clicks, the locations, so the places we go to, some shopping details if we use a credit card, everything is used either by some private companies, or I would say maybe worst case, some national agencies. And this had, especially recently, there was these Snowden revelations, for instance, that showed the scale of this happening. But okay, we see that everything is being tracked, but at the same time, what can we do? Is it necessary that we just withhold all the data? And this is not necessarily true. So privacy is not necessarily complete non-disclosure. And an example of this is that when you go to your tax accountant or to your doctor, you're actually sharing some very sensitive data, and you don't feel as if there's a lack of privacy by doing so, because there's some kind of implicit or sometimes even explicit trust contract between you and your doctor that allows you to feel safe by sharing this information. And at the same time, you realize that if you want the service, well, it's actually necessary to share this information, otherwise you don't get anything. So this is true at the individual level, but this is also true at more collective level. So the society in general would benefit from individuals sharing their individual data points. Medical advances and research has been built on patients kind of willing to share their cases. Surveys for sociological research has built also on this willingness to share your sensitive information to gain insights from it. And some examples, concretely, even when the information being tracked is digital, is, for instance, search engine queries that could identify outbursts of diseases almost in real time. So this is some benefit that any society could want by their individuals sharing their data. The thing is, it's quite challenging, and it sometimes causes massive harm, as we've seen in some cases where companies have shared their data, but it went incredibly wrong. And I'm going a little bit more in the details of some of these cases when I go into the privacy-preserving mechanisms that the people throughout the last decades have tried. So this is an illustration data set that I will use as a base for the explanation. There are several attributes usually in this kind of data set. Some are directly identifying, such as the name, the phone. Others, well, maybe not so much, because many people share some attributes, the birth year, the sex, the zip code. And then there's usually some sensitive information, for here a medical condition. And then sometimes you may have some other type of information that could look cryptic. So for instance, here is just a time series of whether a person had a headache a certain day or not. So just one if yes, zero otherwise. And let's start with the first one. So this is what usually is called personally identifying information. So this is information that could almost directly identify any given person. And if a data set is shared with this information in it, well, basically you have no doubt that it will cause kind of harm directly to the people in it, because it's obvious. And this is exactly what happened in the Cambridge Analytica with Facebook data leak. The information that was got in the first place was voluntary, if we will, by the Facebook users. Was, I think, 30,000 people who gave their personality traits, and at the same time kind of access to their personal data and the personal data of their friends. So this data had the names and a lot of other detailed personal information that this company used later on to build personality profile and then cross with voter register in order to craft highly targeted ads to show again to a large number of people and supposedly influencing the American elections. So what is the solution? Is it just to remove all personally identifying information? And actually, this is widely used today in the industry. Many companies still just use this method, just remove the names and then release the data set. Some call it pseudonymization, some call it sanitization, de-identification, some even call it anonymization. And if we remove this, we remove the first column, then we have the others. And the second type of attributes I would like to focus on is this attributes that are not unique to you, taken one at a time. But if you combine them, as Łukasz said in his previous talk, if you combine them, then you get actually quite unique information about people. So the researcher Latanya Sweeney showed that 87% of Americans are uniquely identified by a combination of birth date, sex, and zip code. So basically, it's as if you are releasing the names. So if this, again, doesn't work either, because if you do this, you can still identify, as I said, the people based on these attributes, and this is exactly what Latanya Sweeney exploited in the Massachusetts Group Insurance Commission, where medical data about state employees had been released. So it was very detailed. It had the zip, birth date, and sex, and then it had all the medical history of individuals. The visit dates, the medication, the procedure, the diagnosis. So this was highly sensitive, and they released it. They just removed the name and released the data set. So what this researcher did, she purchased voter registers. It's publicly available. You can just pay $20 and get the whole file. And she managed to join this voter list that had the name and address with this medical data set. And from this, she managed to build the medical file of the Massachusetts governor at the time, and then she sent him the whole file. Another type of information that a little bit less obvious is this kind of thing. So you have something, for instance, product visits, or some time series about something happening or not, or movie preferences, and you could say that this is not really personal data because many people do the same thing. And I like to think about these kind of attributes as fingerprint-like information. So when you look at two fingerprints from a distance, well, they kind of look very similar to somebody who's not used to them. But if you check the details, you realize that every fingerprint is unique. And this is the same for this kind of information. Most of the time, the more dimensions you have, the more uniqueness is in the data, and the more you need to consider them as highly sensitive as well, or at least identifying. And as an illustration to this kind of attributes, there's the movie preferences. This was a very famous attack on the Netflix prize dataset. So Netflix wanted to get a new, more performant recommender system, so they just released pseudonymous data for their users' movie preferences, and asked researchers to apply different algorithms on them and try the best. And Shmatiko, Vitali, and Narayanan took the data set, but they didn't build the recommender engine. Instead, they went to IMDb and as well took the movie preferences from IMDb. And what they found is that you can you uniquely identify people in large proportions just based on 4 to 5 movies, especially if the movies are not very popular. So here they showed that with 4 or 5 movies, you could identify more than 80% of the people. Even though the data in the first place was just a number from 1 to 5 in different days for a certain set of movies. Another example of another fail is the Strava or Interact. This is more recent. This was early this year. Strava is a running and sport tracking app, they released a service called the heat map, and basically what it shows is where the people run or where the people cycle. And they have 30 million runners worldwide, so they just released these heat maps in all over the world. And as you can see here, well, 30 million runners maybe, but not that much in this area. It looks quite dark. And when you look at in the details, again, you can identify some points that were light in the middle of the desert. And another researcher managed to identify some military bases, and some of them were actually secret. And okay, this is a case of aggregates, but with Strava, you could also identify single individuals. In France, it was possible to identify a secret agent because he was jogging from his job at midday, and then you could cross this with public races times, and because he was tracking the same thing both in Strava and it was also publicly tracked, well, you could just join because it was all straightforward. Many more, of course, and the common issue between all these approaches is that the attack is quite simple. You just need an auxiliary data set, and then you can link your main data set with another publicly available data set or some data set that you find somewhere, either legally or illegally. I mean, if you're an attacker, you probably don't care that much. And this auxiliary data set itself may contain personally identifiable information, which means that you manage to identify single records. So what's the takeaway? The takeaway here is just that pseudonymization is not enough. And we realize that many people are still thinking about pseudonymization when they talk about anonymization. Whenever you hear a sentence such as, "We do not share data in any personally identifiable way," most of the time people are talking about pseudonymization. And yeah, as I just showed, it doesn't work. So as a solution, the same researcher that exposed the Massachusetts governor medical file came up with k-anonymity with the main goal of avoiding these unique joins that constitute the privacy breach. So she focuses on the quasi-identifiers. These are these attributes that are not necessarily unique to you, but they are when you take them in combinations. And then she makes sure that each combination appears at least k times, so that when you join it with another data set, you have k rows, and by doing so, then you're not singling out any single record. And the main techniques are generalization, so you generalize the values, you don't keep the highest level of granularity, and you can suppress the outliers, for instance. And here I'm looking at an example, so the same data set. And we will go from this one here to the left as an original data set to the one to the right as a 3 anonymous data set. So the 3 anonymous means that every combination has 3 records. So for instance, we remove the last 3 digits of a zip code, and then we just suppress the whole sex colon, so we don't care about it, because otherwise we cannot k-anonymize these 3 last records. Okay, so how it works, we see that if we have this person here and we want to check it out or identify it in this data set, well, if we check these combinations, then it can be any of these 3. And these 3, well, they have different medical conditions, so we don't infer the sensitive information about this person. So it seems like k-anonymity worked in this case, except that it works in some cases, but in many others it has some shortcomings. And here I'm showing 2 cases where it doesn't work. There are others, but these ones are the most straightforward. So if I have black born in 65 and female, then it can be either of these three, except that when you check the medical condition, well, they are the same. So you still know that this person has a heart disease, even though there were three people, because all of them had the heart disease. Another one is called the background knowledge attack, is, for instance, this second case, when you have three people, and when you look at the medical condition, the sensitive information, if you have some background knowledge about this medical condition, well, you realize that this person here, male, could only have one of them. And basically, you're identifying the person. So in these cases, it doesn't really work. There are other variants that try to solve the problem, but they suffer from the main issue, which is that this guarantee is mainly syntactic. So it doesn't have any knowledge of the sensitive information it's trying to protect, and or the background knowledge of the attacker. Also, if you have many dimensions in your quasi-identifiers, it's actually even hard to achieve this k-anonymity on its own, so without talking about the background knowledge, because the more dimensions that you have, the harder it becomes to define some closeness between the records. So the takeaway from this one is mainly to just assume the worst, especially for attack scenarios. The attacker is not limited. He can have, or she can have, many information about the data she's dealing with, auxiliary data sets, everything, computational power. So any methods trying to preserve privacy need to take this into account. So now I will try to think more about what can we expect when we try to guarantee some kind of privacy, especially as we've seen, syntactic guarantees don't seem to work. And one of the promises is to say, okay, I'm giving you my data, but I don't want it to have any effect on any analysis at all. It's as if I'm not giving you my data in the first place. It's like you're opting out of the study. But the thing is, if nobody's data has any effect on any analysis, well, there will be no utility at all when you're trying to analyze the data. The second one is more general. So I say, I have a secret, and I'm giving you my data, but I want that the probability of you knowing my secret after analyzing the data is the same as the probability of you knowing my secret before analyzing the data. So basically I'm telling you, I don't want you to learn anything more about my secret by analyzing the data. The problem is that this promise is also impossible to achieve, because if the secret does not concern only me, it's not specific to me, then it can generally be learned from other people. So even if your data is not in the data set in the first place, you can still learn things about your secret, not because your data was in the data set, but because other people had the same secret as you. So it's also impossible to guarantee this. And one trade-off promise is one that states that with or without my data, I want that any outcome of any analysis based on a data set would be almost equally likely. So what I'm saying here is that I want that the impact of me sharing my information will be limited to just the general learnings from the data, not the specifics of my information. And this is exactly the promise that a formal definition of privacy has formalized. It's called the differential privacy. It was 12 years ago. So yeah, not really very recent, but still has limited adoption. And what it states is that you have possible world including your data and another possible world excluding your data. And then you carry some analysis on it and get in a result. What it says is that the probabilities of this result in both cases would be sensibly the same. And if you write it in a nice formula, it just states that the ratio of probabilities is bounded by a small number. And so it's not an algorithm, it's a definition. And in order to satisfy the definition, you can use different mechanisms. I'm here just giving the intuition. I'm not going really into the details either of differential privacy or different mechanisms. I'm just giving the intuition. So one such mechanism that satisfies it is called the Laplace mechanism, and the idea is to add a noise that follows. So this is a random variable that follows the Laplacian distribution. And here on the x, we have the possible outputs, so the possible outcomes, and on the y is the probabilities. And what it shows that if you add the Laplacian noise to a result of an analysis of a query when it's numerical, then this ratio is bounded by a small number, thus satisfying the differential privacy formula. So the advantages is it has a nice theoretical definition, no assumptions about the attack scenario. It's really in the process, so by design and not at the output. And it also has composition theorem, so you could actually compose different algorithms that satisfy this property and still be able to reason about the guarantees and the utility behind it. It has many drawbacks as well. Another one is also the fact of having multiple queries could lead to some situations where if you ask many queries at the same time, you could at some point remove the noise and infer the true answer. Usually it's not that easy to find differentially private mechanism in complex cases, if you don't have numerical data sets or if they have high sensitivity. And one main drawback is the adoption that's still quite limited. So a lot of research is still going on in this, and you should be prepared to kind of stay on top. It's used in data release, mostly for aggregates. So the US Census Bureau uses it for releasing histograms and contingency tables. And it works quite well. The challenge is to maintain consistency between different sets of queries so that they complement each other and you don't have inconsistency when you check the results. And if we want to have to release the data at the same granularity, then it's a bit more tricky. And fourth mechanism I would like to talk about is data synthesization. And one illustration of data synthesization, or the intuition behind data synthesization, is just trying to learn the distribution of your data sets. Here I'm looking at anthropometric data of the US Army, so you have the height and the weight, and I'm checking the joint distribution. So this is the original data, and if you want to synthesize it, you have to learn the underlying distribution, and then you can sample a new element from it. So this is just the idea. The thing is, if you just do it this way, you still are not guaranteeing privacy, because if you know exactly the mean or exactly some properties, you can still infer information about individuals if they have a very large contribution to this result. So one possible way to deal with this is to combine data synthesization with differential privacy by learning the distribution in a differentially private way, and then you can synthesize from it. Yeah, So applications of data synthesization usually, because you keep the same granularity, then you can use it as if it was the original data. So you can use it if you're in software development process. You could use it in development phases. You could use it to limit access to real data if you have sensitive information, and replace it with synthetic data when possible. You could also share it for exploration purposes. If you, for instance, in the Netflix case, if you want other researchers to work on your data, develop models, and then maybe you want to apply it on the real data afterwards. And then some final notes. I think the most important is that pseudonymization is not really anonymization, so just do not use it. I remember 8 years ago I was working on a project, and we actually did this, thinking that it was enough to anonymize the data. It's wrong. Hopefully today the legal constraints and in general also the scandals around data privacy would be a trigger for organizations to consider this question more seriously, and to look for better privacy preserving mechanisms. Yeah, and another thing to conclude is that privacy preserving data release is still an open question for many cases. It works for many cases, but for others it's still ongoing topic. So if you're a researcher or interested in the question, there are still many things to do. Thank you.
Thank you very much, Omar. So, the topic of anonymizing data, or all the nice notions you you displayed. Any questions from the audience to Omar?
More of a request to expand on a theme than a question. So I'm guessing lots of people here are training particular types of algorithms on data sets.
Mm-hmm.
I've seen a couple of attempts to anonymize the data set considering the utility, right? So
yeah.
Given that I am going to use this to train this type of model, I can synthesize around the original data points in this particular way and then delete the originals.
Exactly.
But that's relatively tied to the utility. Is this something that you've been exploring at all, kind of when it will probably be useless for anything else, but for this particular purpose, this data set will actually do well?
Sorry, what was the last part?
So the question is, if you've been exploring also these questions where the data set that gets released maybe to the research team is tied to the utility which they need it for, and would not actually be useful for anything else because it's been anonymized for that utility.
Yeah, it's a very good question, and there are different approaches. So the first one is, if you really know the algorithm, sometimes there are private implementations of the specific algorithm. So if you know that you want to have this task and you know that you want to use this particular algorithm, then you can have this private implementation. There are many algorithms, I don't know, random forest, for instance, or many algorithms that have private implementations that you could use. This is the first point. The second point, if you know the exact question you're looking for, then you can do the synthesization with this in mind, but then you would be focusing on some question, but losing the generality of your data set. And the third case, which is I would say the holy grail of synthesization, is to have a completely generic process that preserves all the properties. So that's what we are trying to do, and it's also an open question. So many people are trying to do the same. The thing is that it's still difficult to have all the statistical property, that the questions. If you cannot, for instance, preserve outliers if you're actually looking for privacy preserving thing, because an outlier is the most sensitive, probably, or the first one to get lost. So this kind of considerations are to keep in mind, but it is possible in some cases.
Okay, we have one question. Let's first start here.
Thanks for the talk. In case of k-anonymity, do you think that if your data set is without those edge cases you showed with the background example, if it's enough, like for you to go with that?
It's the main issue with k-anonymity is that it has the first statement is there are quasi-identifiers. So there are some attributes that we care about. The thing is, this statement is false because all the attributes are actually identifying. And if you're trying to preserve it at a whole at the whole level of all the attributes, I would say it depends. It's not really yeah.
I had more of a technical question about one of your first slides. So with the headache patterns, you said that the higher dimensionality, the more identifiable they are.
Yes.
Which, yeah, I agree. But exactly, this is also the signal that you're after, right?
Sorry.
So this is exactly the signal in the data that you're after.
Yes.
So what's your advice in this case? I mean, should you try to also anonymize this, or I mean, it in itself it's useless without any additional data set which has exactly these identifiers and some other personal data. So I mean, in this particular case, what would you do?
So the question is if you have many dimensions and other sensitive information, right?
Yeah, like in the headache data.
Like in?
In the headache data set.
Sorry, I'm really...
Headache, like headache patterns.
Oh yeah, okay, cool. So the one that I'm using personally for this kind of information is to try and learn the underlying distribution. Hopefully in a privacy preserving way. So you try to this headache data, so you have different symptoms, for instance, over several days, and you try to learn how they occur. And from there, so you're not generalizing or you're not adding noise to specific entries, but you're trying to produce new ones that kind of reproduce the same statistical properties of these ones. So the main point is that you don't release exactly the same, because if you release exactly the same, then you're breaching the privacy of the first person in the first place. But if you manage to learn the statistical properties that led to these values occurring, then you can still learn from it, from the new data set.
Thank you.
Okay, if there are any, maybe we have time for one more question here. And yeah.
I'll eventually become hated by the audience. My question is about one thing which was not mentioned, and I don't know, it's probably quite a naive question, but how far or how viable conceptually is it that data sets can actually be hashed and still remain useful for machine learning in general?
So this is another whole new other topic. I'm not very familiar with the question, but yeah, I wouldn't try and answer on this, but there are things going in that direction. Homomorphic encryption is one such direction where you could hash the data, encrypt it, and then still be able to run computations on top of the encrypted data set. You are most of the time limited to what kind of computations you can still do and to the speed of computations, but it's a direction that's definitely worth exploring.
Thank you.
Thanks.
Okay, thank you very much, Omar, again.
Thank you.